Okay, so we're going to take the derivative again using the definition. So remember, the definition comes from we have a point nearby, and we're making them infinitely close together, and we're taking the slope between the two. So we're going to work this out algebraically, and then we'll check and see if it actually works. Here's a function that's a little more interesting. It's a polynomial or a quadratic. If we graphed it, it would look like a parabola, right? A little more interesting than a line. That was our last example. And so one thing I want to point out is algebraically, occasionally I see people overthink this part. Is what does f of x plus h look like? Boils down to kind of what does a function mean in the first place. A function is a rule or set of rules, and we have inputs and outputs. And so x is just a placeholder, right? It's saying this function saying take our input and square it, and then multiply it by 5, and then subtract 6 times that input plus 4. So we use x as a placeholder, but the input could technically be anything. And so if you feel like you overthink what f of x plus h looks like, one good thing to do is write down your function and just leave an empty space where x is, right? X could be anything. It could be a, b, c, d, e, f, g. It could be 1, 2, 3, 4, 5, 6, 7. I feel like the part that's awkward about x plus h is that you're plugging in a value for x that already has an x in it. So f of x plus h means take our original function, and where there used to be an x, put an x plus h. So here's what it looks like, right? But it does sometimes help to write the framework of the function and then do your plug-in. So this whole thing is f of x plus h, and we need to subtract from that whole thing our original function, right? So that we fit this definition. And so it is all of this minus the original function, which is 5x squared minus 6x plus 4. And then it's all over h. And we want the limit as h goes to 0. So we're doing the difference in the two y values over the difference in the two x values, which is automatically h. It's the distance between these two kind of imaginary points. We're getting them infinitely close together. So this is what f of x plus h minus f of x looks like. Be careful, especially for the minus part, you need the parentheses. All right, so all we're gonna do is simplify this. Like essentially we're done. This is the derivative. Ta-da. But obviously we can clean it up quite a bit. And so we'll just see if we start distributing, getting like terms together, is there anything that's gonna cancel? So first thing to be careful about, eventually you'll get really used to it because it comes up a lot, but x plus h squared means x plus h times itself. So I know it's tempting, but we can't just throw the squared in there. If it's this quantity times itself, see how that requires FOIL? So my first two terms, x times x is x squared. My inside outside are both hx, and my last is h times h. Eventually you'll do so many of these, you probably won't even think about it anymore and you'll just skip right to this part, but be careful. X plus h squared, because of the foiling, is x squared plus 2hx plus h squared. Don't get exponent happy and just throw it in there. All right, so if we're simplifying here, we have the limit as h goes to 0 of 5 times, we just figured out that x plus h squared looks like this. I could probably distribute my minus 6 now. Could wait till later when we distribute the 5, totally up to you. Plus 4. We could distribute this negative, so minus 5x squared plus 6x, right? Negative and a negative, minus 4. This was a little side work. So make some room. And it's all over h. All right, so now I can distribute this 5 in here. And everyone's got a different level of how much algebraic work they are comfortable combining. It's totally up to you. If you notice you make a lot of little mistakes though, the first thing you can do to try to help with that is write out more steps than you think you need. It doesn't matter how well you know it, everyone is prone to little mistakes because you're thinking kind of faster than you're writing, or in my case, I'm talking because I'm narrating these videos. I make little mistakes all the time. All right, so let's see if we got everything. Now we'll see if there's anything that we can reduce or cancel. These always get a little uglier before they get nicer. So let's see, 5x squared minus 5x squared adds to 0, minus 6x and plus 6x, plus 4 and minus 4. And so we're left with like just these three terms on the top and over h on the bottom. So we have 10xh plus 5h squared minus 6h all over h. And if you notice then all the terms have an h in them. So we can cancel h out. Some people like to just cross it out. Be careful if you do it that way. It's only canceling one of those, because technically if you wanted to write out the work for it, what's happening there is that h is a common term on the top. So you're factoring it out of the top. So 5h squared still leaves 1 behind. And then once it's a common factor of the top and bottom, then you can cancel it. Not everybody writes that step out. It's totally fine if you know what you're doing. Just that's why it works that way, so be careful. All right, so now we have the limit as h goes to 0, right? The distance between our 2 points goes to 0 of 10x plus 5h minus 6. All right, so notice this whole time we couldn't plug in h as 0 because we'd be dividing by 0. But once we got it to cancel out of the denominator, now there's nothing that stops us from just plugging h as 0 right there. And so what will happen to that 5 times 0 term when we do? It will go away. So the limit of this is just 10x minus 6. If you take h to 0, that term disappears, and so you're just left with this. All right, so then let's zoom out a little bit, because it's easy when you get bogged down in tedious algebra to lose the forest for the trees. This is our answer, but what does it mean and what did we just do? So we took this function up here, 5x squared minus 6x plus 4, this parabola, and we found the derivative, which represents the slope at every single point of this function. So we just figured out the derivative function is 10x minus 6. We did that using the definition of the derivative, the whole thing about taking 2 points, taking the slope between them, and then taking the 2 points to be infinitely close together, taking the limit of the distance between them to 0. So that idea again. If we want to see this in action, just to test a couple points, right? There's no like proof by testing cases, but just to kind of see it work, we could go graph our original function and make sure that like, if we pick a point like x is 1, the slope over here should be plug in 1, 10 minus 6 or 4. If we plug in x is 2, the slope should be 10 times 2, 20 minus 6, so 14. So we could just try some points on here to make sure we're convinced that it works. So here's our function, 5x squared minus 6x plus 4. Here's a graph of it. And here's a random point, right? 1, 3. It looks like a positive slope there. It looks like a kind of steep positive slope. And since we have it calculated over here, the slope at that point, if I plug in 1, is 4. And notice like if that fits in our derivative, our derivative was 10x minus 6. So our derivative, if we plug in 1, is 10 minus 6 or 4. Do a couple other ones here. So let's say if we plug in 0, we should get a slope of negative 6, right? 0 minus 6. If we plug in, let's say 2, we should get a slope of 20 minus 6 or 14. So really steep. So let's move our point and just see if that works. So if I put in 0, and this one's doing 2 points technically infinitely together, you can't put them on top of each other in this calculator, so we'll be a little smarter than the calculator here. It says negative 5.99999. I think that's calculator speak for negative 6, right? They have to approximate this too. You can take the exact derivative in these, but this tool is set up to just do a slope, so it's still got 2 points that are really close together to make it work. And for 1, 3, we get a slope of 4. Let's see, for the point 2, zoom out because it's a little far up here. We should get a slope of 14. So the point 212, we end up with a slope of 14. So it's nice after you get it to see it, to see it in action. We'll look at that idea a lot more in the future, but in terms of just taking a derivative, going from a function to its derivative, using the definition. If it's a long function, it can get a little tedious, but it's nice to see it does work.